6:30. Mr. Edgar!
Ideal gas law. You guys remember from chemistry that the ideal gas law is can be remembered as... Wait, where did it go? No, where did it go? Oh, there it is. Oh, it's blank. As probably my favorite formula to say of the entire year. Now, for some reason, chemistry and physics teachers don't often refer to it this way, but it makes it so that it's basically impossible to forget. And that is, the ideal gas law is known as perv-nert. It's a perv-nert. Don't be a... Wait, PV equals nRT. PV equals nRT. All right, now where does that come from? Well, it's a combination of the three gas laws we discussed the other day, Charles, Boyle's, and Gay-Lussac, and Amedeo Avogadro's recognition that that the relationship between volume and moles is the same for all gases. Now, if we start with PV is related, write this down, PV is proportional to the temperature. Check. That means if we divide by temperature, PV divided by temperature in a certain situation would remain constant in a closed system. So if I were to write that as PV, this constant, if that constant is equal to N times R. Now, N stands for the number of moles, and R is simply a constant. So now, what is that constant equal to? Well, divide by N, the number of moles, and you get PV divided by NT is equal to R. Now, I played the little unit game here. Pressure, you guys know, is measured in Newton meter squared. Oh, no! Oh, I just gave it away. Volume is measured in meters cubed. N is moles, and temperature is Kelvin. That all comes together to a Newton meter per mole Kelvin, which we also call a joule. Now, I was just about to say, okay, everybody, get your calculator out. Let's see what that value for R is, because there are some things that we know. So take a moment and write these down with me. First of all, at STP, at standard temperature and pressure, I'm going to say that the pressure is 1 times 10 to the 5th pascals. Now, the actual number is 1.01 something something times 10 to the 5th. But at STP, we're going to let pressure be 1 times 10 to the 5th. Now, it is known that the volume for 1 mole of gas at STP is 22.4 liters. But in physics class, we're not going to use liters at all. We're going to use meters cubed. So there are 1,000 liters in 1 meter cubed. So the volume will be 22.4 times 10 to the minus 3 meters cubed. Temperature for STP is 273.15 degrees, or 273.15 Kelvin. And the number of moles is going to be 1 for this calculation. Now, to solve for R, I feel bad that was shown already, but let's plug it in. So if I get PV divided by NT is equal to R. Now, our values are going to be a wee bit off because of some rounding issues. We'll wave our hands over it at the end. So I got 1 times 10 to the 5th pascals, 22.4 times 10 to the minus 3 meters cubed, divided by 1 mole times 273.15 Kelvin gives you R. All right. So now what? Well, plug it in. Do it. You know where I learned that move? Dan. I learned that from Dan. So R, if you punch it all in, you know what you get? You get like 8.2 something. And that's because of the rounding, because the actual value for the ideal gas law constant is 8.31 joules per mole Kelvin. Now, I make a big deal about this because in chemistry class, you used different units. You did. Now, were they wrong? No, they weren't. But you weren't dealing with joules. And I got to tell you this, when we start doing thermodynamics and the study of heat flow, one of the things we're going to look at is conversion of energy. And we measure that in joules. So we're going to use these units that are given. In chemistry, you may have used for pressure ATMs. For volume, you use liters. For temperature, actually, you still use Kelvin. For R, you used a value of 0.0821 ATM liters per mole Kelvin. Does that number look familiar to any of you? If it does, it's not wrong. It's just using a different set of units. Let it go. Let it go. So, what I'd like to do now is to go through some examples so you can see again how to use the ideal gas law. Got it? I'm going to push pause. If you guys could get that packet out and turn to where the gas law examples are, and we'll pick it up with the pogo stick question. We're back. All right. So number 5 says a child's pogo stick. By the way, this is a rich kid's pogo stick. My kid's pogo stick just had a spring in it, but this one's fancy. It says a child's pogo stick is filled with compressed gas. If the toy has a pressure of 2 times 10 to the 5th pascals and a volume of 3 times 10 to the minus 3 meters cubed at 293 Kelvin, how many moles of gas does this contain? Well, you can see I already took the liberty of drawing a pogo stick. Here's the gas, and it gave the details right in the problem. It's just a plug-in chug. So the ideal gas law says that pressure times volume is equal to the number of moles times the gas constant times temperature. Since I'm trying to solve it up for N, let's get that all alone. Let's try that again. Let's get that all alone. Let's plug in our values. 2 times 10 to the 5th times 3 times 10 to the minus 3 times 8.31 times 293. Now, I didn't show the units there. If I could go back in time, I probably would show how they all cancel out nicely. Feel free to rewind this and watch it again. This time with the units crossed off. Oh yeah, that's not how time works. All right, let's see. What you guys get? Anybody else get 0.246, or I'm going to call it about 0.25 moles? Yeah, good. I just wanted you to do a practice problem where you had to use that. Number 6. A mini CO2 cartridge, like those ones that you use with paintball guns. They're about yay big. We will assume has a volume of 80 milliliters. If the cartridge is left in the sun and has a temperature of 20 degrees Celsius, what would be the pressure inside if the cartridge is only partially full with 2.5 grams of carbon dioxide? So number 5 is easy, and number 6 is not. There's all sorts of things going on here. What the heck? So you know what I'm going to do? Stall. There's a picture. And we've got carbon dioxide bouncing around inside. All right. And it gives me some information. Let's see what we've got. It says the pressure, is what we're trying to find. The volume is 80 milliliters. All right. The temperature is 60 degrees Celsius. And the mass is 2.5 grams. And the molar mass is equal to 44 grams per mole. Now, some of you are salivating because you're so excited that you get to go back to chemistry. Sweet, me too. PV equals nRT. And in order to find the pressure, I first need to find the moles. So you know what? I could do it all in one step, and if you want to go ahead and do that, go for it. But I am going to take a moment and do my dimensional analysis on the side. And start with, I've got 2.5 grams of carbon dioxide. Now, if I want to get rid of grams of carbon dioxide and go to moles of carbon dioxide, I've got 44 grams and 1 mole. So, 0.057-ish. I'm probably not going to round that when I punch it into my calculator. Okay. Now, the only other thing I've got here is some conversion factors. Now, for volume, 80 milliliters. I might as well do that right here, too. I've got 80 milliliters. I want to convert that to meters cubed. Now, milliliters on the bottom, liters on the top. Milli, you better know, there's 1,000 milliliters in 1 liter. Then, I keep going. I want to get rid of liters and go to meters cubed. Well, a liter is a decimeter cubed, so that means if we took a cube that was 1 meter cubed, and I broke it up into decimeters, so there was 10 on each side, then I would end up with 1,000 liters in 1 decimeter cubed. So my volume is actually going to be 80 divided by 1 times 10 to the 6, or 80 times 10 to the minus 6 meters cubed. For temperature, it's going to be 273 plus 60, or 373 Kelvin. All right. The ideal gas law is the easy part. It's the conversions that are a serious pain in the neck. So if we get N all alone, I've got PV divided by RT yet again equals, no, I'm looking for P. Focus. Sorry, Jake, that was embarrassing. This is you when you usually bail me out with a joke. This is not as much fun. P equals nRT divided by V. So the number of moles we already found, it's in your calculator, 0.057-ish times 8.31 times 3. Oh, you guys were chomping at the bit for that one, weren't you? 333 Kelvin. Divided by the volume, 80 times 10 to the minus 6. And you get, punch it in, we're all going to wait for Dan this time. Then we'll be waiting forever. Never mind. Abel, did you get 1.97 times 10 to the 6? Or we'll call that 2 times 10 to the 6 pascals. Is that the answer is on the bottom of the page? I don't see it. Oh, it says 19.4 ATMs. Moving on. Number 7. I don't know, convert that. I think that's right. Actually, I think it... I'll check later. Number 7. If it's not right, you do realize that I have to go back and shoot this whole video again. Number 7. A piston sealed with a movable piston contains 8 times 10 to the minus 3 meters cubed of oxygen at 30 degrees Celsius and 2.5 times 10 to the 5th pascals. How many moles of gas would this be? This one's a lot easier. P V equals nRT. PV divided by RT is N. I'm going to be quiet for just a moment while you guys plug everything in and get an answer. I got 0.794 moles. Now, next says, how many molecules is this? Oh yeah, we're going back. We're going back, baby. Capital N, capital A subscript. You guys recognize it? That is Avogadro's number, which is 6.02 times 10 to the 23rd anything per mole. So 6.02 times 10 to the 23rd. So for oxygen, let's see if I have, so that was review. That wasn't my problem. So if I have 0.794 moles of oxygen, and I know that for every mole, there's this many molecules or atoms, depends what we're talking about, 6.02 times 10 to the 23rd. What do you get? Did you punch it in already? Joel, I know you already got an answer. Stop yelling at your computer, Joel. Mom's going to get worried. I got a 4.78 or 4.8-ish times 10 to the 23rd molecules. All right. How many grams of oxygen is this? Now, I gave it to you. You see it? I wrote it as O2. Why? Brinkelhoff. Whenever you find oxygen in its gaseous state, it's always going to be a diatomic molecule, so it's going to be O2. So then when it says one oxygen atom has a molar mass of 16 grams, then one oxygen molecule, which is just two together, is going to be 32. So how many grams of oxygen is this? I'm going back to the moles. So I got 0.794 moles of oxygen. I'm going to put moles of oxygen on the bottom, grams of oxygen on the top, and it's going to be 32 grams per 1 mole. 25.4 grams. Now, for some of you, this was review from chemistry. For some of you, this was relearning it from chemistry. For some of you, you don't remember it at all. I would say gas laws are kind of like an intermediate step for us in order to solve these really interesting thermodynamic problems down the road. So I took the time today to go over the ideal gas law, practice with a little bit of chemistry,